Hello everybody, I'm Brian Shiro from the University of Hawaii, and I'm here to talk about geological activities going on at the High Seas Analog Mission Simulation. High Seas stands for Hawaii Space Exploration Analog and Simulation. Before I start, I'd like to acknowledge my co-authors Kim Binstead and Scott Rowland, also at the University of Hawaii, as well as to others, Jim Rice and Sarah Fagins, whose work is also involved with this, and the crew and the research team, and NASA Behavioral Health and Performance, who actually funds the project. So this project is geared toward human health performance in this remote environment specifically. So as we venture farther into the solar system, the time delay gets greater, as of course you know. So in fact, there are anecdotes from astronauts at Apollo where even the 1.5 or so second delay was disrupting to their activities. And as we heard earlier this morning from Jake as well as from Darlene this afternoon, time delay is a priority for NASA, is understanding how this could work for surface operations. So at High Seas, we take this to a bit of an extreme, and we are specifically tasked with studying crew autonomy. And the ground is very much hands-off with the crew. We try to have minimal interaction with them. And this is all constructed under the assumption of a 20-minute one-way communications delay to simulate a Mars mission. So just a bit about analogs. They're wonderful for discovering problems you didn't know you had. So when you test equipment in the field, you go out there with the real world elements, things happen. Things break, you have to fix them, you have to innovate. It's a wonderful way to iterate on your design, whether it's your operation, whether it's your technology, whether it's your strategy. And so analogs are a very important component of our exploration strategy as we bootstrap our way to the stars. So why High Seas? Why did NASA create another analog? So High Seas is specifically tasked to mitigate long duration and high latency missions. It's a wonderful test bed for this. So one of the reasons for that is because we have a high fidelity habitat and location. This location in Hawaii is a compromise or a sweet spot between being very remote and being very accessible. So there are wonderful analogs at other places such as the high Arctic and Antarctica, which are great, but they're remote and expensive to reach and hard to reach. Other analogs are closer to home, and there's trade-offs with all these. But Hawaii is nice because you're only an hour away from the nearest city or international airport. Also, High Seas has astronaut-like crews. Some of the same people involved with the astronaut selection at JSC are involved with the selection of crews at High Seas. We use some of the same processes that they use. For example, we had 700 applicants for 6 slots at the last mission, so it's pretty high selectivity there. And because this is a NASA Human Research Program project, this is all about tracking crew cognitive and team performance over time. And one of the tools we use to do that, and why I'm here today, is geologic field tasks. So we have the crews going out doing EVAs every day, and this is one of the metrics we use to track how they're doing over time. Just to give you a sense of the High Seas mission timeline and scope, there are 4 missions that are funded. We've already finished the first one, and the second one ends in 2 days. So if you haven't been following the mission, I encourage you to go to the website. You can learn more about it. And there are 2 more missions coming up, an 8-month and a 12-month. So this is going to get longer and more difficult. The previous 2 were 4 months each. Just tell a bit about the habitat because it's interesting in its own right. It's a geodesic dome, hemisphere. It has 2 floors inside with the crew habitation upstairs and the common spaces downstairs. It's completely outfitted with sensors that measure temperature, humidity, carbon dioxide, air pressure, and other things, in an artificial intelligence system that regulates all this. So the engineers really had fun building it. It's one of the few smart structures that are in existence. It was modeled after one at Stanford. So if you're interested in that as well as the power systems, I'm sure they would love to talk with you about it. It's completely powered by solar with fuel cells. So let's talk a bit about where it is. So High Seas is on Mauna Loa at approximately 8,200 feet elevation. It's in an old quarry site, which is the quarry they used to build the road up Mauna Loa, if you're wondering. What's great about this is the site was already disturbed and it was already leveled off, and it made the environmental impact for permitting the site quite easy. And it's very little vegetation there. So it looks like Mars, of course, and it also helps with the psychological aspects for the crew, which is one of the important parts of the mission. And it's on historical flows, most of them from the mid-1800s to the early 1900s, and various types of pohoihoi textures there. Many other interesting features of note, including skylights and lava tubes within easy walking distance of the habitat, vents and cones as well. So we have the crew walking around with these things exploring. So how does the mission operation work? Well, kind of like you heard earlier today with the other analogs, we have a ground team, which is the science backroom as well as mission support people who serve as communication conduits to the crew. And what we do in the geology science team, we come up with the task that we're going to give to the crew for the week. And then we send this task to them. This is all over a 20-minute one-way communications delay. It's all text-based, chat-based kind of system that we have. And then the crew receives this. They think about it. They ask questions. They have questions. They come up with a plan for how to implement it. And then the crew sends us their plan. And if we approve of it, then we let them know. We have a few constraints and guidelines they have to follow, safety-related. They can't go in certain areas. They have to constrain their EVAs to 4 hours or less. They have to always have a buddy system, basically. So we look for red flags like that, but so far they've been very good about staying within safety parameters. So once we approve it, the crew goes out and they do their EVAs, and we don't micromanage the project too much in the sense that we don't tell them we don't tell them how to do it. We tell them what to do, but not how to do it. And so the mission commander has full leeway to decide which crew members go in which EVAs, who's going to stay back in the habitat as the IV crew member, what the roles are going to be as well. So the crew carries out the tasks. They decide how many EVAs it's going to take, for example, and they come back and report to us. We look at the reports and the data, and we decide on the next one and iterate that way. This whole process generally takes about a week. So what are the tasks like? Well, they're all team-oriented because this is primarily a psychology-related project. So we want them to interact, and we want to track those types of interactions. They're progressive in that each task builds on the previous one, gets more complex, as well as follows in a logical sequence. And they're all gradable with quantifiable metrics. That was very important for us. So we save all the data about the time, about the distance, about their expected time, and their actual time in different places, as well as the accuracy of their interpretations for their results. And I already mentioned about how we tell them what to do, but not necessarily how to do it. And this is all couched in terms of resource exploration and environmental characterization. If you were landing on Mars and you knew very little about your area in detail, how would you go about exploring it? That's what we keep in the back of our minds. So I want to walk through some of these tasks to give you a sense of what it's like. So the first one at the beginning of the mission was we wanted them to explore this feature next to the habitat. See if the laser works. Yes, so the red dot is where the habitat is, and there's this long northeast trending volcanic line of scoria cones there. And so to get the crew out, get them used to their equipment, we had them get the volume of the feature. So they had to get the perimeter as well as the height at different places and estimate the volume. They did a great job with this. And so we built upon this with the second task to get the density of the material comprising that. So they went out and they actually collected 29 samples at different representative places throughout the cones. They came back to the habitat. They measured specific gravity, which is a comparison between the dry weight and the wet weight. And what's great about this is because we now know volume and density, therefore we know mass. And this is essentially we've characterized the ore body at a high level. We know how much is there. We know something about its vesicularity now as well. And if this were an ore body you were going to mine, say to create insulation for your habitat, you would know what you're dealing with. To round out that study area, we had them also draw a geologic cross-section. And I just wanted to echo one thing that was mentioned earlier today. This crew does not have a geologist on its crew right now. The first mission, we had 2 professional geologists. And we noticed some of the same lessons that were mentioned this morning where when the projects that were led by them as field PIs, and I like that term, they would get very detailed. And they were great projects and reports, but they were lengthy. Whereas we've noticed by training the crew beforehand to do these things, and yet they're not geologists professionally, they're engineers mostly, they actually are more efficient. And they always surprise us with how efficiently and actually how high quality their results are. You can see their little cross-section there that I came up with. So we moved on to another area. This one was a little anomalous in our task in that this one did not involve an EVA component. In this case, we had the team interpret aerial imagery. We gave them visible, near-infrared, synthetic aperture radar, and multispectral images, and had them interpret a geologic map based upon this. This was mainly for them, for their benefit, to gain experience with that. But what was interesting is we decided to make it a team activity in that we had the crew members do it separately and then come together and merge their interpretations together and capture how they made their compromises to come up with that interpretation. There's an example of one of the maps shown over here on the right. The next logical step, though, was to go out and actually ground truth that map. So the next task, we had them going out there to verify that the units they identified and the boundaries, interfaces were there where they expected them to be. They looked for superposition evidence and came up with a relative age sequence of the units and refined their map. They actually reduced, simplified it slightly, and it was a very good job. So I mentioned earlier there were a lot of lava tubes and skylights, and so we had them create a comprehensive catalog of lava tubes and skylights within the study area that we had defined. And they went out and they measured the heights and width and depths and condition of the floor and of the ceiling and the volume inside and whether it was safely entered and what the azimuth of the tube is, if it has a tube. Some of these are the things that they measured. They actually identified 13 skylights that were of note, about half of which were accessible in their estimation. You can see some photos here. I like this one because it shows someone inside looking up at one of the crew members outside. So another task, this one, they just completed this one this week. This was an emergency task, and so we actually put their catalog to good use. So they know where all these skylights are, they know which ones have lava tubes, and they have guesses about which ones are probably safe. Well, then we threw them a monkey wrench and we said, there's a solar particle event coming your way. You better go to your, and by the way, their safety procedure in such an event is to go to a lava tube. So they had to gather all the emergency supplies, and they had to find out a strategy to get it there safely. And along the way, they actually evaluated 2 different tubes and chose one of the 2, and they put all the equipment in. And what was interesting is this paralleled a hurricane that was coming to Hawaii. It luckily dispersed, but they were worried about rain and things like that along the way. You can see the crew members here inside. Now, I didn't mention the suits earlier. They have 2 types of suits. These are the less high fidelity ones, the lower fidelity ones. These are just hazmat suits. The other suits you've seen in some of the pictures, the white ones, are from the University of Maryland Spacesuit Lab by Dave Aiken, the ones they use at Desert Police. One of the aspects of some of the data we're collecting in all these EVAs is GPS, and we have the crew create very detailed EVA plans where they plan their traverses and estimate when they're going to be in different features of interest. And then they of course, measure their actual tracks and times, and we're comparing that right now. And it's one of the metrics we're using to compare performance over time. Do their estimates get better with time? Is one crew better at it than another crew? And if so, why? That's some of the things we're teasing out of this. So going forward, next month we're going there to do some field work to ground truth these tasks further and create more tasks for the other missions because they're longer. And we're going to enhance the fidelity of some of these tasks going forward for the next missions. For example, we have a rover plan for the next mission, which is going to enter these tubes and map them with LiDAR. And that's an example of an opportunistic research study. And I just wanted to call your attention to the opportunity that's out there now for any researcher. If you want to collaborate with the project, you can send us a short proposal, just a few paragraphs description of what you have in mind. And if it works well with the project, we'll consider it. So if you have an EVA type system that you want to test, or you have some type of research that may complement what we're doing, you're welcome to do it. We have several dozen projects that are involved in one way or the other. And the final goal is just to improve understanding of autonomous crews under situations of high latency to help us on long duration missions to places like Mars. Thank you.
All right, good. We got time for a couple questions. Anyone have any questions out there? No? Okay, thank our speaker again. And this closes the Human Exploration and Destination Driver session.